All right, guys, let's do practice day 5. This one is a challenging one because the concepts are not as intuitive. The second problem of these is similar to what we saw with the angular motion one on practice day 4. The first one is more dealing with springs and friction. So let's take a look here. Our first question here is the long free response question. This is the one that you would get 25 minutes to do. And we're told that this block is at position 0, the equilibrium position basically, which is what this indicates, no force on the block. So that means it is at the mid position of its equilibrium and its motion as it goes back and forth on this. There is friction. This is not a frictionless situation, so the friction has to be accounted for. So that means if it's going to the right now, there is friction going to the left, and it's a kinetic friction in this case currently, and so the spring is pushing it, but there's no force right there. The instant it goes past this point, the spring will be pulling it back. So the friction force and the spring force will be in the same direction in a moment. Right now, there's no spring force. And if it were to the left of this point, there would be spring force acting against the coefficient of friction, or against the force of friction, I should say. We don't know what the coefficient of friction is. We do know that it does have a velocity here, so that it's kinetic friction right now. So those are some things to pay attention to, some little details as you look at this. You can make notes or do different things like that to give you an idea what's going on. So for part A, at that instant, when the block is located at that point, moving to the right, predict the direction of the net force on the block. So if there's no force from the spring, then, and I would say there's still gravitational force downward, but there's still normal force from the counter, or the whatever surface it's on, which are both equal and opposite. So there's zero vertical net force. The only force acting on it right now is the friction force. So that is to the left. So we want to justify that. So since the spring is not putting force on at this instant, but the block is still moving, the only force acting on it is friction, which is in the opposite direction of motion. All right, something like that would be sufficient for explaining that. Then this is a challenging setup here. So here's a graph that indicates the force exerted on the block by the spring. So this is Hooke's law. And you could use your memory or your equation sheet, which is F equals kx, that tells us that the displacement x, the bigger the displacement from point 0, the bigger the force that returns it towards that. So this is point 0 right here. So as we can see, the force from the spring at that point is 0 because x is 0. But as it goes in the positive direction, the spring gives a negative force. All right. And as it goes in the negative direction, the spring gives a positive force. So that's what this this line represents. That is Hooke's law in a graph form. Now it asks us then, on the same graph, draw a graph of the net force on the block as a function of position x for situations where the block is moving toward the right. So if it's moving toward the right, there is a force in the opposite direction, which would be the negative direction from friction. And if it's moving, that means that's a kinetic friction force, and kinetic friction force is a fixed amount of force. So what we would have is a constant force in the negative direction as long as it's moving to the right, and that would be added to the spring's force to give us a net force. So we would end up with something like this. We just subtract a certain amount. And the difference at this point, and you don't have to describe that or anything, is the friction. Because what we saw in our earlier setup is that even at that point, there is friction. So we have to have a negative force acting at that point if we want to be consistent with our answer above. Now, if we look then, the question is the graph you drew in part B consistent with your prediction in part A? And I would say yes. Okay, and the claims for Y. The friction is a constant negative force while the block moves. And that is added to the spring force to give net force. All right, so I would think that that would be enough to go with. You could expand on that. You could say the varying spring force, add it, subtracting the opposite direction kinetic friction force would give us this graph. Okay, now keep in mind that on our test this year, we're not supposed to have to do graphs. We're not supposed to have to do drawing. So some of this stuff you wouldn't have to do, but you might have to explain. You won't have to do free body diagrams. I think the next question here is a free body diagram. But we have these different situations that we have to face, and sometimes explanations are what we have to settle on. So now we have the same situation, except the spring is moved, it's been displaced, and we're told it's come to rest. So if it's come to rest, that means there's a force from the spring, Hooke's law, in that direction. And if it's at rest, that means there's force of friction, Fk, in that direction. And if you remember, Fk is equal to mu k, or no, if it's at rest, it's not k, it's s. So let me get rid of that and put s in there. Mu s times the normal force, which is equal to mu s times mg. All right, so those are the forces acting on this block right now. We also have gravitational force and normal force. Keep that in mind. So that's what this is asking. First thing here, on the dot below, which represents the block at the rest and to the right of x equals 0, draw and label the forces. So we would just do Fn is straight up. All of these forces would be equal and opposite the force equal to the opposite direction force, I should say. So this is my friction force, static friction force, holding it in place. And this is my spring force in that direction. All right, now derive an expression for the maximum displacement possible for the block that will allow the block to still remain at rest. Express your answer in terms of m, k, mu s, and physical constants as appropriate. So we have this. This is kind of our guiding principle here. We don't have to worry about the vertical forces, but the horizontal forces we have to worry about. So F of the spring has to equal Fs, static friction force. Now, F of the spring is Hooke's law, Kx, and static friction force is mg, or the normal force, which is equal to weight, times mu s, because it's static. So we're looking for x, right? Expression for maximum displacement. So what we have to do is mg mu s over spring constant. And that would tell us how far it can be displaced before the static friction force is overcome by the force of the spring. So there is where we have to make sure we understand the forces acting on that block. Moving on to question number 2. We've seen questions kind of like this before. I know we did one earlier in the year in some of our practice problems, and we did a similar one in practice day 5, practice day 4, except for that one was dealing with angular motion, angular momentum, and velocity. This is not dealing with angular motion. We don't have to worry about angles and things like that, other than the fact that we're looking at how far the pumpkin swings up. So we're told this arrow is going towards this pumpkin, which is going to serve as kind of a pendulum. We're not going to have to worry about, looks like right here, we don't have to worry about the periodic motion of the pendulum or anything, but this arrow strikes the pumpkin, and there are 3 different scenarios. Theta embedded, so the arrow strikes and hits it and the pumpkin swings up. The arrow passes through, the pumpkin still swings, and then the arrow bounces off and the pumpkin swings. So what we have to do is rank the 3 angles, embedded, pass through, and bounce, based on which one has the pumpkin go highest. So that is based on the conservation of momentum and the fact that the arrow is hitting it at the same speed each time means that the total momentum of the system is the combined momentum of the arrow and the pumpkin. The pumpkin has no momentum initially, but after they collide, they both have to add up to the same momentum that the arrow had originally. So what we have there then is the ranking system. What we need to compare is what's going on in each of these situations. So if that pumpkin is hit by the arrow and the arrow sticks in, then the combined mass of the pumpkin and arrow have to have the same momentum that the arrow initially did, which means that the velocity is going to go way down and it's going to swing up, but it's a combined mass, so it's going to have a lot less height than some other situations. if the arrow goes through it, it's going to have, the arrow will still have momentum to the right, and the pumpkin will still have some momentum to the right, but they still have to combine to give us momentum that's equal to the arrow's initial momentum. So the pumpkin will have less momentum than it did with the combination of it and the arrow. So it will move slower, therefore not as far up. And then if the arrow bounces off, it reverses momentum, which means it has a negative momentum. The pumpkin has to have a positive momentum that adds to the negative momentum to give it overall positive momentum equal to what the arrow had initially. So what we have here then is that the bounce will have the highest angle, the embedding will have the second highest, and the pass-through will have the third highest. And we have to put that into words then in this. So since momentum of the system is conserved, the combined momentum of the arrow and pumpkin stays constant both before and after the collisions. In the bounce situation, the arrow has negative momentum because it changes direction. So the pumpkin must move fast in the positive direction to have extra positive momentum. That will cause it to move the highest angle. Okay, now I want to talk about the second situation. So that's when the arrow is embedded. The combined mass of the pumpkin and arrow will move slower after the collision but since they must have same momentum, it has the next highest angle. The lowest angle occurs when the arrow passes through the pumpkin, because the momentum of the arrow is still a large proportion of the original momentum. So the pumpkin has limited velocity, which means limited angle of motion. All right, there's a lot of different ways we can word this. I used more sentences than I'd like to, probably, but you don't want to go too much more than that. Okay, so you don't have to go into huge detail, but you do want to talk about the conservation of momentum and the fact that those have the same momentum before and after the collision, and how those momenta compare to each other in how they affect the pumpkin's angle. Keep working on these. If you have questions, we'll get together on Wednesday before the exam. I'm going to have a Zoom meeting on Wednesday, so I'll send out a announcement via Schoology so we can get together and have some questions and answer session. Hopefully these things are going well. Keep plugging away. Have a great rest of the week. Thanks.